So to finish off the electric fields portion of the gravitational electric and magnetic fields unit, we're going to talk about a very famous experiment called the Millikan oil drop experiment. And basically what this experiment is about is we were trying to determine what is the smallest possible charge that an object can have. And we've actually already seen it in some previous questions. I will show you how this was measured, and this is another important experiment in the history of physics. So it says here that at the start of the 20th century, physicists still had many questions about charge of fundamental particles. So a big question was, is there a smallest unit of charge that nature will allow? And if so, what is the value of this charge? In 1909, physicist Robert Millikan set out to examine the existence of this elusive fundamental charge using a series of experiments. So the basic idea here is, if there is a fundamental charge, then we would know that there could be nothing smaller than this charge. And all charges would then be multiples of this singular charge. So it's kind of like turning electric charge into a discrete measurement rather than a continuous measurement. So Millikan hypothesized that an elementary charge, E, the smallest unit of charge in nature, did exist, and that the charge of the electron was equal to this elementary charge. So his hypothesis was that there is nothing that has a smaller charge than an electron. And he set out to solve what is that smallest possible charge. So please copy this down. Millikan was trying to answer two questions. What is the smallest unit of charge? Is there a smallest unit of charge? And what is the value of this charge? And his hypothesis was that there is an elementary charge, and the electron is equal to the magnitude of this elementary charge. So what he created was a device that would essentially have an electric field between two charged plates, and he would have a set voltage, and then he would be able to determine, he'd be able to kind of alter his epsilon and make a charged particle stop. And when he found the stopping value for that charged particle, he can then determine what the charge was. And he was hoping that once he found all this data, he would end up finding some sort of relationship. If there was an elementary charge, then each kind of data point he would get would have to be a whole number multiple of that fundamental charge. So I'll read this a bit more because I didn't talk about how he made these charged particles. And what he actually did was he shot small droplets of oil into a container from an atomizer. And this atomizer basically picked up these different oil droplets would pick up different charges inside of his apparatus. If it picked up, say, 5 electrons, then the charge, after kind of balancing this out, the charge would have to be 5 times the elementary charge. And if it picked up 1 electron, then the charge would have to be 1 times the elementary charge. So to measure the charge on the drops, he used an electric microbalance. This is the general idea between this, right? So if you remember how I was mentioning earlier, epsilon is similar to your acceleration when we're talking about the big gravitational world we experience. And if we had a force of gravity acting on an oil droplet, it would be F equals mg. So he would determine the mass of the oil droplet based on the size of the sphere that it creates and the density of it. You don't have to go this far in depth, but basically what he did was he finds the mass of each oil droplet after he gets it balanced. He knows the density of the oil, so he determines the mass of the oil drop. He now knows the Fg that's acting on the oil drop, and there has to be a counteracting Fe that is equal to the Fg. And that counteracting Fe can then be put into the electric field intensity equation, Fe equals epsilon Q, and he could find out what the Q is. So here's again, this is showing it a bit more in depth. So the plates were connected in such a way that the magnitude of the electric field and therefore the electric force on the droplets could be adjusted. By adjusting the electric force to balance the downward gravitational force, Millikan could bring a charged drop of oil to rest in the region between the plates. So there's an Fg pushing the oil drop down. There's an Fe that is pulling the oil drop up. If it's balanced, the oil drop will almost levitate. It'll be suspended. So we can understand how Millikan used the electronic microbalance to determine the charge of an oil drop by comparing the electric and gravitational forces. So basically, he sets Fe equal to Fg. Fe is Q epsilon. Fg is mg. So he also knows that epsilon is delta V over delta D, so the potential difference divided by the displacement. And he can put these together to create this equation. Now, you will not be using this equation on a test, but it's important to know this equation because it might help you solving questions related to Millikan's oil drop experiment. So it says to measure the mass of the drop, Millikan simply switched off the electric field and observed the final speed of the drop as it fell into the bottom plate. From the final speed, he can calculate the mass of the drop if he accounted for both the gravitational force and the force due to air friction. So it's a little bit different than, I think I've described it how it was done in experiments that are done currently. This experiment gets replicated. You might even replicate this yourself if you take physics in university. So it's replicated quite regularly, and there's a bit more accurate ways of determining that using very good microscopes. We can actually see the volume of these very small oil drops, and that kind of helps to solve this. Millikan repeated this experiment many times, balancing a drop, measuring the voltage, letting the drop fall. He ends up getting a series of data, and from that data, he notices that there is an elementary charge. Each of the data points is basically this elementary charge times a whole number. So he then determines the whole number, or the elementary charge, as 1.602 times 10 to the negative 19. So he could basically determine how many electrons the oil drop picked up by observing what its charge was, dividing that charge by this elementary charge. And this elementary charge shows up on your formula sheet. It's listed as E. Now, we've been talking about an electron, but the elementary charge is actually the charge of a proton as well. Whereas the electron is negative, the proton is positive. I'd like you to copy this down, but just know we're not going to use this equation in mathematical problems. You might be using it to describe something. And as such, we're not going to go through these example questions, but feel free to try them out. They shouldn't be too hard. They're either rearranging the equation or just solving the equation based on what it is. So, while Millikan was successful in discovering and measuring the fundamental charge, there was some controversy with his experiment. So he expressed the time for the oil drops to fall or rise to an accuracy of 1/1000th of a second using a stopwatch. And that was not possible in using the technology he had at the time. So this is just bad science. And this is partly why we should use significant digits. He was basically expressing his answers with greater accuracy than the tools with which he was using, which caused a lot of people to kind of disregard his data and his results. Another problem was the extremely small drops bumped into one another, which not only affected their rate of fall, but those of the other oil drops as well. So in the early experiment, there were some problems. There was also the fact that he disregarded a large set of oil drop data in his experiments that did not agree with his hypothesis. And you should never really disregard data. All data is valid. If it's not agreeing with the hypothesis, you have to figure out why. It's either the hypothesis is wrong or the way the data was taken was wrong. So please write these down. I won't repeat them, but you may pause and copy down some of the problems that Millikan had with his initial oil drop experiment. I won't go through how it was fixed, but I did kind of mention a little bit of that to you. So if you feel like you need to answer that, add that to a question that you're answering, you can do so. Next, we're going to talk about the charge of a proton. So we mentioned that an electron and a proton have the same charge. It's just the electron's charge is negative, the proton's charge is positive. But an electron and a proton are very, very different. An electron is very small. Its mass is of the order of 10 to the negative 31 kilograms, whereas a proton is almost 1,000 times larger than that. It's of the order of 10 to the negative 27. And the proton itself, being much larger, it's actually made up of different materials, whereas the electron is more of an elementary particle. It's not broken up into others. So this question says, an electron and proton are situated in an electric field. Will the magnitude of the electric force on each be equal? And it will, because they have the same charge. It's just that one is negative, one is positive. However, the next part of this question asks, will the acceleration on each be equal? And it will not, because the mass of the proton is much larger than the mass of the electron. So the electron will accelerate faster than the proton. Now when we get into Unit 5, we're going to talk about what makes up a proton and an electron. Why does an electron not break up into other particles? And just to kind of scratch the surface here, the proton is itself a combination of 3 different quarks. And the quarks do not exist on their own, but quarks have charges of 1/3 or 2/3 of the elementary charge. And when they get combined together, they end up having they give what they've created, the proton in this case, a total charge that is equal to 1. There is no situation where the quarks will exist and give you a charge that is 1/3 or 2/3 of the fundamental charge. But if we look at them on their own, they do have that, although quarks do not exist on their own. So despite having fractional charges, no experiment has detected any combination of quarks in nature that have a total charge whose magnitude is less than E. For this reason, physicists still refer to E as the elementary charge. So in fact, every subatomic particle that researchers have so far detected has a charge whose magnitude is equal to a whole number multiple of e. Researchers also believe that the amount of charge in an isolated system is conserved like energy. Unlike energy, electric charge does not come in different types and cannot change from one form to another. No interaction can destroy or create electric charge, and the total electric charge of the universe remains constant. So with that, that's the end of this lecture. Please review the lecture, and you do not need to do the questions from this part. I don't even think it shows up on your homework sheet for the course, but if it does, you'll not be doing questions, the math type questions that are assigned for this section. So do not complete those. They're not assigned for this course.